So you know real quick. Okay, so now I'm going to test with this. Unfortunately, I'm not going to turn this around. I was going to see, can you operate that from there now?
What buttons do you use?
The arrow buttons.
Oh, wait.
Yeah, we did each other. That's not a big deal. It's interesting. I think I could just use this board until we get into quantum. Okay. First thing, you'll be happy to know that the book actually tries to subdue the math as much as possible. And I forgot back when I picked this text, that was one of the reasons, because we have a very diverse group of people that learn this. So it tries to stay on track as much as the physics. So that means some of the more difficult topics we're actually speaking in terms of from a conceptual standpoint, and more qualitative than quantitative. Okay, when we get to some harder stuff. In that way, this is kind of the junior version of NAPR's P10 course. So if you enjoy this, you can feel free to take all the math and rigor that he introduces his stuff in. One of the questions I do have is how many people have computer programmed before? Obviously, Drew, you have. Drew, do you know the program Monkey, M-U-N-K-I?
Not I have, but
Yeah, somebody need to talk about it afterwards, because I might have a project for you. But anyways, has everyone programmed at all?
I did in high school.
But that's it. Wait. No? Alright, we'll probably steer clear of that. There are a lot of programming activities, just simple things that you can write for numerical analysis of some of this stuff. So, unless I can really simplify it, I'll probably avoid those. Okay, so, the year is 1905. That's where we're going to start. That's where the entire text starts and the entire concept of this stuff is. And it was an interesting time to be a physicist. In fact, this is, kind of the year of, you may have heard of this name, it's a famous year that Einstein came out with his theory of special relativity. But he was actually chastised for becoming a physicist, as all physicists were at the time, because everyone was told that all the hard problems of physics had been solved. Between Newton and Maxwell, they had solved everything. There was just a few things to clear up, and then everything was going to be, done. And physics would be done. Wasn't 15 years later that it realized that everything we thought we knew, we don't understand anything about. So everything changed quite a bit. There was a couple of problems that existed at the time. One of them was the rate of precession of Mercury's orbit was off a bit. So in other words, Newton had correctly predicted the orbit of Uranus, except it was slightly off. And they thought, well, it's only off by a little bit. So the assumption was that there's another planet out there pulling on Uranus, and that's why the orbit is slightly off. Otherwise, Newton's mechanics were perfectly sound and everything worked. Then he predicted where Neptune was, and that turned to be spot on. He defined Neptune. Okay, so everyone has got 100% belief in Newton and all of his ideas, and everything works just fine. Then he turned to Mercury and was trying to look at Mercury's orbit. Now, Mercury is getting further away from the sun. Boy, I should know this precession. I believe so. Mercury is slowly getting further and further away from the sun. I'm positive that. One of the two. Closer to the other. And this precession, as it goes farther away, can partially be predicted by Newton's mechanics. And the problem is, it was slightly off. And it was off by enough that nobody could really explain why. I mean, we're talking like a couple percent. In any class, it would still be fine. It would be an A, experimental error. But there was no experimental error on this. The reason there isn't much experimental error when you get to these large systems is because you have these different planets that have a certain amount of mass that act like their center point. Okay, whether one tree falls down on a planet is not going to affect how the planets are interacting with each other. So 1% off in terms of planets is huge. It's not like when the planets are out today. Oh, there was a large intergalactic wind. What? That doesn't make any sense. There's a whole lot of nothing in between here and the planets. So we should be able to predict the orbits with the extreme accuracy. And they couldn't do this, so this was a problem. And one of the other predictions, the reason that they said that Uranus's orbit was off was because they thought there was some mystery planet that we can't see that was too far away, some other celestial orbiting body that is pulling off gravity, etc. Okay, that is not the case for Mercury. We know everything in between here and the sun, and there's nothing else going on. So that was perturbed some of the physicists at the time. Things that were going well were Maxwell's equations. So Maxwell's equations are everything that dominates electrodynamics and magnetism. So if you take that course with me, that one is incredibly math intensive, probably the most one that we have. Maxwell's equations turned out to be extremely complete and really did a nice job of defining everything that was going on with electricity and magnetism. It worked pretty well. In fact, they're the only system that is still considered complete today. So anyway, can you guys tell me the four forces, the four basic forces in physics? You guys remember? Yeah.
Gravity, weak, strong, and the last one.
It's the one I'm talking about right now.
Oh, the electron.
Yes, Coulomb's force. So you got strong force, which holds nucleus together. You have the weak force, which is in terms of radioactivity. We'll get to that, maybe. And then you got gravitational force. So the gravitational force is actually even weaker than the weak force. But the only force that is considered to be completely explained is Coulomb's force. Okay. Maxwell's law predicts that incredibly well. And it's still holding up today, so that was good. But there was still one problem in that. Light. Light was a problem. Light's a problem because light is propagated. We can see light, it goes from one side to the other. We turn on a flashlight over here, all of a sudden we can see over there. Light has moved, okay, and it's propagated. And the question was, what is it propagating through? So what's propagating through air, just like sound or anything else? Well, we also know light propagates through space, okay? We have sunlight, and somehow it gets here. And as far as we can tell, there's not a whole lot going on out in space. So there's this big question as to what light was actually traveling through. The other thing that was a big question was the photoelectric effect. So all these things that I'm mentioning right now is precursors to topics that we're actually going to cover in the class. So all of these mysteries that were slight issues at the beginning of the 1900s that started to get bigger and bigger and bigger were then solved by either special relativity or quantum mechanics for the most part. All right, so the other one was the photoelectric effect. This one was kind of neat. Light can knock electrons off metal. So if you've got a sheet of metal and you shine a light at it, you can actually get electrons off of it, and you can measure a current, a sizable current. So even with technologies that existed at the turn of the 20th century, this could be measured. The problem with this is standard theory, standard Newtonian classical mechanics states that, all right, light has a certain amount of energy. We got that. We're good with that. So a certain amount of energy hits the metal. It's going to excite the atoms. It's going to excite a certain amount, and a certain amount of electrons are going to come off. Okay. So what do we do? Let's turn up the intensity of the light, and in theory we should get more electrons off. Just amp it up. It turned out that that didn't work. If you amp up the intensity of the light, you didn't get any more electrons off, which was really confusing. And in fact, it turns out that you turn the intensity extremely far down, and extremely low levels of intensity, and you still get a current off the metal. So it's entirely independent of that. Nobody can explain why. The other thing that Thompson, I forget if it was Thompson, the person who actually discovered the largest correlation between what controlled the amount of current that was off, found out that it had to do with the spectrum, the wavelength of the light. So whether or not we're shooting 400 nanometer light ahead or 700 nanometer light ahead, that's what made the larger effect. Okay, so if you had this light wave, and back at the turn of the century, they didn't exactly have a single spectrum or single nanometer wavelength that was really impossible to use. But let's say you've got something going like this. So here's your wavelength down here, and then you've got your intensity high up here. Okay, so if we've got a wavelength down here, we'd say that if this was the dominant spectrum, or the most likely the peak nanometer wavelength, if that coincided with the work function of the metal, then you get the most light. So they would find as they shifted this, if they shifted to red light or to blue light, all of a sudden they'd get a whole lot more electrons. And the neat thing about it was, yes, they could use extremely low intensity light, but if it was at the right wavelength, all of a sudden they had these electrons. So nobody understood that. Okay, the other problem, Equipartition theorem. Anybody remember what that one is? You two got this. It's equipartition theorem. Hey, where were you?
It's called Fitted. What's the rest of it over? So I ran the job for a little over. You record the train line.
Yeah, sure. Yeah.
That's also why I was less concerned about being 10 minutes late.
We were just talking about how everyone encouraged Einstein to stay out of physics in the turn of the century. 1905. All the problems were in 1905. David, do you remember what the equipartition theorem was?
Partition there?
Equipartition.
Oh, wait, you talking about the two-dimensional box thing?
No. Not that I know. What do you got? Who knows?
I remember writing it.
Wait, you talking from physics or from PChem?
It's the same.
From which material is that? Regarding the one?
We covered it in physics. We covered it in, well, those of you that had me for 2211, which you did.
Technically, actually. Is the thing about, you know that graph right there?
No, this is, no, that was,
Yeah.
has to do, it's thermodynamics.
I don't know.
Oh, you didn't have any for that? No. That's what you have. Okay.
Is the thing about the 50% on one side, 50% on the other side, one thing was slightly different?
No. Okay, so the idea of the equipartition theory is saying that for any particle that has a degree of freedom, it has 1/2 kBt. Okay, in terms of energy. Energy is 1/2 the Boltzmann constant times the temperature of the substance has. That's how much energy it has. So when we talk about at the molecular level, and I want to know what energy an individual particle has in a gas, what do we say that it has? Remember the equation for energy of a gas particle in terms of its temperature?
Maybe that's from chemistry, not from physics.
Okay, it's just 3/2 kBt. I'm guessing you guys at least recognize that equation.
We recognize it.
Lie to me if you don't, please. All right. So you had me for intro physics. Did we get through thermodynamics?
I think so. I mean, first equation was familiar.
Okay.
Dr. Ross,
The second one is actually should be more familiar with the first. Oh, we got.
Students got through it, so I know you guys got through it.
Well, no, but I switched it around because I started doing fluids at one time. I forget which class he was in. We did fluids in the class. Anyways, point B, equipartition theorem. When this came out, and I'm terrible about names. Yeah, I don't even have written names. The idea being is that an object will have this much energy for a given temperature depending on its degrees of freedom. Now, what is a degree of freedom? Basically, it means what direction it can move. So if a particle in a gas can move in 3 dimensions, okay, it's pretty straightforward. That's why it has 3 times this, it has 3 degrees of freedom. Okay, now, a solid, how many degrees of freedom does a solid have and why? Yes. What do you got? 1? Nope. Nope. You do. 6. And then 6. Why? Anybody want to guess as to why it's 6? Not 3, not 2, not 0, not anything else. What ways can you have energy? What are the 2 major types of energy to begin with? In introductory physics, we teach 2 types of energy for the whole
Kinetic.
and potential. Okay, so kinetic energy. An object is a solid, can be moving, and have a certain amount of kinetic energy. Okay, can it have potential energy, and how? What is the difference of an object in a liquid, in a solid, or a gas in the first place, other than its temperature?
The amount of energy in it.
Yeah, but what happens when something is solid?
Structural, it's
Trying
held in place.
It's held in place by what?
Bonds.
Bonds. Okay, it's those bonds that have potential energy. So you'll often see people draw, a solid, but draw a picture like this. So you got some object like this, and it's got a spring this way, a spring this way, a spring this way. And you see this giant glass network of a whole bunch of springs. It looks like a giant mattress. Whenever I see that, that's what I think of as for the mattress commercial. So an object in there is bonded to the other atoms around it. So what ends up happening is, yes, it has a certain amount of kinetic energy that's going around like this. It has that amount of kinetic energy. But here's the thing. When it has the amount of kinetic energy that's going this way, what it's also doing is creating spring potential energy, which is not truly a spring, but bond potential energy, and the bond across it, and it's using bond potential energy across here. So it's no different than the single harmonic oscillator when we looked at this. We had the box on the spring like this. We said, how much energy did it have? Well, we know how much potential energy it has it here, how much kinetic energy it has it here. We add those up. So in a solid, you can do the exact same thing that you can do in a gas, and you can say, all right, well, I can still move in all three directions, but now I've got springs in all three directions. Okay? So you end up with 6 times this, or you're going to be 0, 2, 3 dt. Okay, and I don't mind going over any of the old stuff. This class is much more informal than the other, so it's not a big deal. So yes, the energy of a solid is this. Now, in terms of, when we talk about energy of a solid, how can we measure this? Or what is the other term usually used for energy of a solid? Let me put it this way. If you had a choice between aluminum foil that you put over your pan when you took it out, or steel foil, which would you choose and why?
Aluminum.
Aluminum, why?
Malleable. You can.
Well, there's that too. You might never get the steel foil off. Do you ever notice when you take aluminum foil pan out of the oven, you put it on your oven, you can touch it practically instantly.
Conductivity?
On the edges. Conductivity actually has very little to do with it. I can't say none, but little.
How much energy it can store?
Yeah, what is that called in the solid? There's a word for it. What are those?
See, I would say charge.
Something, something at constant pressure, something, something at constant volume.
Oh my gosh.
I don't know if it's STP.
I'm not telling that. You had PHYS, right?
I'll drop.
Oh, you got it.
You know, I meant before.
Well, I can only tell that.
Yeah, I meant 4 weeks.
Specific heat. Specific heat. Or heat capacity. The specific heat of an object determines its heat capacity. So, objects have a certain amount of heat capacity. Aluminum has shit for heat capacity. It can't hold a temperature to save its life. It just can't hold on to heat. So the neat thing about it is when you pull something, you don't pull lasagna out of the oven, and on the edges, the aluminum will be super cold, it'll be just room temperature, and the center it'll be just as hot, because it can't hold on to heat. So it instantly turns to whatever temperature the surroundings are. Never use it as insulation. Terrible idea. So, where was I going with that? I know what I want to talk about here, but I forget what I was talking about. Oh, okay. So the idea being is that this determines the amount of energy that a particular solid can have. Okay, and then there's this shows right here that 3/2 kBt is talking about the temperature, but this doesn't include the heat capacity of the object. So then, if you want to talk about a particular object, type of object, you put in the heat capacity. Aluminum's is shit, and then it says how much energy you can store. Great. So when they came up with this theory, they started testing it, and for solids at room temperatures, at normal Earth temperatures, everything worked out fine. All of a sudden, they could predict the heat capacity of all sorts of different types of materials. This was great until things started to get cold, like really cold. Okay? We're talking colder than freezers. And then they started testing heat capacity, and all of a sudden, they found out that things had the inability to hold on to heat, like beyond. I mean, all of a sudden, you've got this prediction where this should be a linear system like this, and it went bam, and there was just a clip that fell right off. Which turned out to be a great thing, because once we discovered how this works, what did this region help us create?
Superconducting?
Yes, superconductivity. We found out something that has the inability to hold heat all of a sudden. I mean, what happens, like, why do you have different wires that are rated at different gauges? Because it's a certain amount of electrons you can jam through there before the thing sets itself on fire, right? If you can then create materials, and crazy weird materials, like carbon and things like that, that you would never throw current through first. All of a sudden now, if you can create it cold enough, it becomes superconducting, can't hold on to heat, and electrons basically travel through it instantaneously. So, at the time, nobody was thinking superconducting magnets, they're just thinking this graph doesn't make any damn sense. So this was one of the other problems that we'll get into. So that was results of the equal partition theorem. Everything was great and wonderful until they started looking at low temperatures, and then they couldn't answer anything, so that was a real problem. And it was only for solids. That was the other thing. It was only for solids. So it had to do with the bonding strength in here, the potential energy and how that functioned. Okay, next thing, atomic spectra. This was and we're starting to get to the point that physicists start to realize we really don't know what's going on so much. Okay. Does it say on there?
What's the heading of this chapter section that we just did?
What's what?
What's the heading of the chapter section we just did?
This is all part. Well, okay. This is all the introduction chapter. We're going to get through chapter 1 and the beginning of chapter 2, and the chapter 1 just talks about some of the topics that are in there, plus whatever my brain decides to add to it, or random things I've read. Then we'll get into chapter 2. We're just going to go lengthwise through the book. So, I think it's a pretty decent book, or I hope so. Last time I taught this, we had heroin. All right, so this line spectra. This is particularly for a hydrogen atom. So this was something else that was curious. So as we started to progress now, we're getting a little bit past 1905. And the interesting thing is, I'm going to come back to 1905 and we'll talk about what Einstein actually came up with there. But it didn't really matter so much because Einstein came up with this idea and 90% of people said, that's retarded. And then we moved on. It wasn't until as the century kind of progressed that people said, he's on to something there. And started to prove true. But in line spectra, this is another weird thing. Okay, if you've got atoms, now that we have the capabilities to actually take spectra of different things, if we can excite a hydrogen or helium gas, helium was more likely, probably not so much hydrogen, but in the other case, they were finding out that it would emit certain wavelengths, very certain wavelengths. Why? Why can't it just vibrate? The molecules that are vibrating faster emit light with higher energy, and the ones that are emitting lower with lower energy. Would that just make sense? That was the theory, and it wasn't that case. And in particular, well, actually no, because they were able to do hydrogen because they had hydrogen lamps. Hydrogen was one of the ones that they could produce the most specific lines, and they had these lines on it. And there was 5 lines. 5 lines. What are these 5 lines called?
Unity states.
Yeah, but what is this called? It's a series.
Wait, you went to the bottom, top, or bottom one?
Well, they're the same in the sense that this is the emission spectrum, and the top is the absorption spectrum. In other words, they're the inverse of each other. Hydrogen can absorb all energies of light except for the ones that it emits. So you could do the experiment either way. It was still mind-boggling as to why this was happening. So hydrogen takes in all the energies and spits only these ones back out. Now, who was the guy who discovered this? Who was credited with this and thought he found the whole hydrogen spectrum? No. You're getting close. Balmer. This is the Balmer series. Okay. Now, it turned out that not only is this pattern here, this is a repeating pattern. So in other words, the spectrum was found originally, I'm just going to freelance it. Let's say it was found here, like that, and that was in the visual spectrum. Well, it turned out that if you shift farther down and if you have equipment that can measure it, you'd find, oops, if I can possibly draw this similar, you'd find another one down here. Okay? And in fact, it turns out that the Balmer series was what number in the entire electromagnetic spectrum?
Okay, 330?
No, so the Balmer series was 2. Okay, and so then this would repeat on and on and on and on. It kept going, and kept going, and kept going. And in fact, if you actually get in here, these lines get infinitely close together. It turns out that there's an equation that actually governed all of this and found all these things. Have I got that name? All the names. Rydberg's equation. So Rydberg's formula. So this first series was known as the Lyman series. The second was the Balmer. The Balmer is the most famous one because that's actually in the visual spectrum. You can see that. And then it goes on to Bohr and then Brackett, and I have no idea any of the ones after that. But it's a repeating pattern. So this happened way after that. They finally figured out that all this was going on. Back at the turn of the century, our simple problem is we've got these lines. Why don't we have just continuous light? We just have lines. We have no way to answer this. So we were trying to work this out. The other thing that was interesting is around this time, electrons were known. We understood electrons, okay, going around an atom. Okay, before the idea of the nucleus, before the idea of protons and neutrons, what were the electrons going around? Anybody, did they have this before? Well, this is pretty well. Okay. Electrons went around and around in goo. It was positive goo. That was what was considered was going on. We don't really know why electrons went around in circles, but it was just they were all around in positive goo. That's what balanced everything out, and everybody's fine with this. Okay, it wasn't until, what, some 15 years later, wasn't it? Yeah, because Rutherford came up with a new model of the atom and had the nucleus on there. But even with the discovery of the nucleus, we still have this giant problem of, okay, the electrons are going around and around the atom. Okay, if they're going around, now we're going to draw back to your ideas of centripetal force. If they're going around, does that mean that there is acceleration or no acceleration? And how do you know?
If it's constant, there's no acceleration.
Okay. How or why?
Or
Something in centripetal motion. Is there a uniform centripetal uniform centripetal motion, which is to say that the velocity is constant? Is there an acceleration? Yes. Constant velocity, yet there is an acceleration. First of all, anybody remember what that? Whenever we do Newton's second law, we write that down as. But instead of acceleration, what do we write here? When we were using uniform centripetal motion.
Not to do with direction.
Has to do with the velocity of the object going around in a circle. So your nucleus here. And we said we can calculate the acceleration if we know the velocity because it equals.
Centripetal acceleration? I don't know.
Yeah, what is it? V squared over R. Remember that? Really?
All of this comes back after you say it.
V squared over R. So we can solve anything that's going in circular motion. Let's do this. Now, the better question, and this one's conceptual, so you got no excuses on this one. This one doesn't involve equation. If something's going around in a circle, even though it's going at a constant velocity, how and why am I making the statement that there is an acceleration?
Because since the electrons are going, but since the electrons are positioned stable, they're constantly acting together, causing it to force accelerate, right? By minute amounts, right?
No, it's not minute amounts. It's an amount that's measurable. In fact, the acceleration is measurable. It's equal to this. So the faster you're going, the better. What do you got here?
it's changing direction.
Changing direction. Okay. So remember this when we said that acceleration, I always try to push on you guys, is either a push or a pull. It's constantly that. Okay, so if you're going around a curve, it takes an acceleration for you to do that. And you can even feel that in your car if you're going around a curve. You can't go around a curve at a constant speed. You actually have to apply the gas to do it. I suppose on the highway, you can kind of go at a constant speed, not including friction. You have to apply an acceleration to stay in centripetal motion because you're changing directions. So in this case, the acceleration is entirely just due to the change of direction. Okay, anyways, the whole point of all that is if there is an acceleration, that guarantees us that there is a force. There's a force that is pulling us into the nucleus. Okay, and the question became, why doesn't the electron collapse into the nucleus? And this was a really difficult problem. And this is well before the strong force or the Coulomb force. Well, the Coulomb force was understood, but nevertheless, the attraction between the positive nucleus and the electron really is mind-boggling. Why doesn't this just collapse in? It's got all this energy. Why doesn't it go around? Why wouldn't it be sucked inside? So that was yet another problem. Okay, so all of these ideas, I mean, they're individual problems, but the two things that explain all of this are violations of Newton's classical physics. Newton's classical physics rely on a whole bunch of stuff, but among those two ideas, one, space and time are absolute, which we're going to show is not the case, and two, everything is either a particle or a wave. I mean, Newton's physics says a lot of things, but those are two things, space and time is absolute, and everything is either a particle or a wave. And we thought we knew this. We thought we were pretty confident in that. And the fact that all of these problems can be solved by just saying, nope, those two things are wrong, really was not well accepted. Okay, it was not. Nobody was willing to jump on that bandwagon right away. Okay, so solving these problems in modern physics are difficult for three reasons. Your book mentions two of them, but I want to add a third one to it because this one was really huge at the turn of the century. One of the solutions, all of the solutions to all these problems run counter to our intuition. Okay, and we're going to see that real quick when we start talking about special relativity. I think it's really cool, partially because it's difficult for me to wrap my head around it. Okay. I mean, the rest of physics, it's like you say that, and you're like, oh, okay, I get that. This stuff, I mean, you guys are quite possibly smarter than I am. Maybe you'll just say you get it instantly. To me, it still fascinates me. It's really cool stuff. But that's also part of the reason that it isn't accepted right away. If you can't just intuitively say, that makes sense, I'll take that, No, I mean, if you sit there and talk about wave particle duality, and we'll watch some videos later on in class. You know, a particle goes through a slot, unless you're looking at it, then it goes around the slot. Just kind of waiting, you can't see it, just because you're looking at it. That is not intuitive. I can't wrap my head around why that's the case.
So this is the box thing.
Huh? I don't know the box. Okay, you have to try to explain it to me later. But anyways, okay, so that's the first reason. All the solutions are non-intuitive for the most part. The second reason is that all of the observations you can't see with the naked eye. Newton had it easy in the sense that, okay, I predict I predict that Neptune will be here. Go look for Neptune. Hey, it was there. Awesome. Okay, so you can actually visually see all these things. Whether or not I want to see an apple, I can time it based on my calculations as to how long it should take to the ground. I mean, with a decent timer, even back then, it should be pretty easy to see whether or not I might. You can see these things. They're extremely easy. The other thing, they already do. Like a cat. In any case, the third thing, which was a really huge thing, is that all of these things require technology to answer them. Okay? And so to measure the speed of light, for example, what's the speed of light?
3 times 10 to the 8.
Hey, we got an answer. Well done, yes. 3 times 10 to the 8 meters per second. And we'll talk about that a little bit more at the end of the day. Measuring that, that's kind of flippin' fast, okay? It's difficult to measure. So on top of things that aren't intuitive, and you can't see them, and those two things actually go hand in hand. The fact that you can't see them and they're not intuitive really make everything difficult if you want to propose something and say, hey, here's my crazy idea. I have no way to prove this. Just go with the math says so. And the third thing was we didn't have the technology to test any of this stuff. And that was a really, really hard part. So a lot of the things we're going to be talking about here in the early chapters, like we'll start Tuesday next week with the Michelson and Morley experiment, is brilliant scientists doing nothing else other than coming up with some sort of apparatus to measure crazy ideas. These ideas are there. How do we measure them? Yeah, all right, so. Okay, so that was the other thing that I was going to mention. So we talked about intuition. A good example of intuition. In intro-based physics, whether you're in 2201 or 2211, one of the most difficult ideas to get across to students is that motion does not require a force. Since the world around us involves so much friction, we're constantly used to friction. We're used to anytime we slide anything, anytime we do anything, eventually an object comes to stop. Why? Because physics says so. No, physics doesn't say so. Physics says there's a lot of friction with that table. And the idea is on a truly frictionless surface, an object will just move and just float along forever at a constant velocity. That something at a constant velocity doesn't require a force. Now you guys all got that eventually, I assume. You guys all saw my floating astronaut through space and whatnot with all that. That's right. No, you didn't. Okay. And it's only 2 of you actually had me for an intro. Interesting. All right. So you saw my floating astronaut through space. So it's that idea that the intuition says that, no, an object that is moving must have a force acting on to it. Not true. Hopefully we've got that done. That, compared to the stuff we're going to discuss in this class, is child's play. Everything is going to be non-intuitive, so it's a little bit more difficult. Okay, so, next thing. Where's the diagram? Oh, there it is. You may have seen this diagram before. Each of the 4 of these represents a different section of physics. All right, so someone pick a quadrant and let me know which. Describe it. A branch of physics.
Quantum mechanics.
Okay, that's one of the squares. Which one is it?
Okay, we're going to go with small and fast.
Nope.
Small and slow.
Small and slow. So up here, small and slow is quantum mechanics. Quantum mechanics. We got your.
Would large and slow be like astronomy?
Yes, but what do we call that in general? What governs all?
Astrophysics?
What?
Astrophysics?
Sure, but something bigger. Who discovered? We've been talking about it most of the day already so far. Who came up with it?
Newtonian.
Yeah. So everything in here falls under the category of classical mechanics. Okay? Classical physics, Newtonian mechanics was all described everything slow and large, which was perfect because everything that we can see with our naked eye generally falls into this category, with one exception: light. And light is what kind of spun all this. What else do we got?
Wait, is fast and small theoretical physics, or that's still quantum?
Not theoretical. No, theoretical is too general. Theoretical covers just fine. Jared, you pick one.
So fast and small, that would be,
That's the hardest one, I'll tell you.
oh, okay.
Fast and large is an easier one.
That's just kinetics.
No, kinetics would be better for mechanics. It's our next chapter, actually. It's special relativity. So, fast and large is everything that falls under the category of special relativity. So,
Is fast and small like light spectroscopy?
no. Even light falls into the category. Well, light can be explained here and here. This one is they just cheat, and this one is relativistic quantum mechanics. Relativistic quantum mechanics. Okay. So that is the really, really beefy one. And this isn't even discussed until the last chapter of our textbook, we probably won't get to. Okay, this is new cutting edge stuff. This is where you get to unifying theories and string theories and things like that that put everything together. Now, what's interesting though is in 1905 we had this. We had classical mechanics, and we started to come over to this region here and say, hey, look, stuff isn't being explained by what we want. And when we started coming over here, we said stuff isn't being explained by what we want. What we're going to show in this class is that there is a theory of special relativity. Special relativity actually explains everything that is in this box, and quantum mechanics actually explains everything that is in this box entirely. Okay, it's only when we get out to this range that both of them necessarily break down. So the point being is that a lot of people, you'll talk about classical mechanics and special relativity being a special case where things get fast. That's not the case. That's not. I should use that word. That's not the point. Special relativity, it perfectly explains motion down here where things are large and slow, all right? It's just the equations are a little bit larger and you still get the same answer. Same thing with quantum mechanics. Quantum mechanics can explain everything that's large and slow. The equations are larger than necessary, so everything breaks down. It's just like kind of every time we do a problem involving gravity, we say that F is equal to m times the acceleration of gravity. Why? Because we don't really feel like right now that F equals g m1 m2 r squared of the Earth and putting that in every damn time. Okay? For most of the problems that we're dealing with the special case of near Earth, and it makes it nice and easy. In theory, technically, we should be using the giant equation every time, just in case we move off Earth or something like that. So that's the point. It actually turns out that classical mechanics is a special case that only really describes motion of a very narrow range of both sizes and speeds. Okay, and we'll do that. We'll do some examples when we get special relativity of big and slow things, and we'll see that we get the same things that we would if we used our normal equations. Now, our normal Newtonian equations. Next question is, there are two types of relativity. What are they? I'm pretty sure that both of you guys have all heard of these two terms. I gave you one, special relativity. What's the other one? General relativity. You've heard that. So general relativity and special relativity. Well, if nobody can come up with that term, I highly doubt everybody's going to be able to tell me the difference between the two. All right, special relativity, and you can tell everyone that you're not studying special relativity, not general relativity, but special relativity, because it makes it sound more important. But general relativity is actually the hard one. Special relativity is the really easy, small little thing. Special relativity is talking about things that we're talking about, things that are moving very, very quick. I found a good quote online. I liked it a lot. It says, special relativity says, how things happen can look different to people in different places or moving at different speeds, except for things involving the speed of light in a vacuum. Things moving at the speed of light always move at the same speed compared to you, no matter how fast you're moving. So it's basically different things seem like they're happening at different times. That's special relativity in the topic of our next chapter. General relativity, which we won't get into, I don't even think it's taught here, unless Simmons teaches it in his classical mechanics, but I doubt it. General relativity says that space and time are actually different aspects of the same thing, two sides of the same coin. Space-time is curved. Exactly how curved space-time is at any point in the universe depends on how much gravity there is in the area. In addition to bending space-time, gravity can also bend light, radio waves, and all kinds of other stuff. So that's where you get to general relativity. You're talking about this whole idea of bending space-time, and when you start talking about wormholes and things like that, and telling a spacecraft can't go faster than the speed of light. So instead, if you want to go from point A to point B, this is real. We're talking about folding space-time such that we will just go here. We'll take the shortcut. And we've only gone that speed, but we've just shortcutted all this because we folded space-time. And how do you do that? Well, by creating a large gravitational pull someplace to cause it to bend. So gravity will bend space and time. Gravity can actually bend light as well. That's all general relativity. And larger than the scope of this course. John Wheeler had a good quote. It says, matter tells space how to curve, space-time tells matter how to move. And that summarizes it. It doesn't explain anything, but that summarizes how general relativity works. So in case, I'd hate for you to come out of this class and not know the difference between general relativity and special relativity. All right, moving on. Special relativity. Okay. So, the idea of special relativity is things that move fast. And we're going to generally stick to large things that move fast. Now we're into chapter 2. Now, how fast? Okay.
Faster than the speed of light.
No, because that doesn't happen. So it has to be comparable to the
That
speed
we
of
know.
light.
Close enough.
Fractions of the speed of light. All right, so let's take a guess. For those of you guys that heard me talk about my Hall thrusters before, what is the typical speed of a Hall thruster attached to an engine? What's the exit velocity of a Hall thruster?
So like 300,000 seconds? Where that?
Well, you got to have more units in there.
So 1/10 the speed of light.
That would be incredibly fast. It's not so bad.
300,000 kilometers.
1/100 is more like it. So the idea being is like 40,000 miles per hour. Okay, so that and that is really moving. Now that's linear speed, and that's actually pretty much about the max that we can do with a linear speed. Now orbital speeds we've gotten a little bit higher. Okay, so there are the Helios 1 and Helios 2 missions. I don't know if you guys have heard of these.
I'm probably gonna get this wrong, but wasn't that stuff to the sun, basically?
Yeah. Helios kind of gives it a little bit away, but yeah, totally give you credit for that. It was, and it was old. It's 1974. These things were moving. These things were orbiting the sun, and they got really close to the sun. When I say really close, by really close I mean 3.7 million miles away. But that's really close. You still don't want to be that close to the sun. So even at 3.7 million miles away, so it was orbiting the sun, and in order to stay in orbit, it had to maintain a speed of 150 miles per hour. So this thing is really, really, really moving. So then, and to date, that is the fastest moving man-made object. But that is about to be trumped. In 2018, NASA is launching something, Solar Star, what's it called again? Solar Probe Plus. Okay. Oh, I'm sorry, no, it's the Solar Probe Plus that's going to go to 3.7 million miles. So it's actually even going to be closer than the Helios 1 and 2. So this Solar Probe Plus, which is going to be launched, is going to be put in there, and it's going to be moving 450,000 miles per hour. So yeah, it's really moving. But even at that, and when we do the math on that, so if you take it in your calculator, you say, okay, 450,000 miles per hour, you have to convert it to meters per second. So that doesn't really help anything. But you're still talking about 100 to a 200th percentile of the speed of light. You get 450,000 miles per hour. Not enough for relativity to even come into fact. Okay. So this is the reason that we don't generally see this unless we're dealing with light. Light is the only thing that we really see in our day-to-day lives that is affected by this. Relativistic effects are negligible. So we need to start talking in terms of 1/10 of the speed of light. Okay, so we want to talk about velocities that are greater than 0.1 c. There are effects below this because obviously it tailors down. I think linearly, I'd have to think about that. But in any case, for everything that we're interested in, we're going to be talking speeds that are about 0.1 c and above, where the relativistic effects really start to take effect. Okay. Okay, so first thing we need to talk about some basics. We need to get some terminology under our belt. First idea is the inertial reference frame. Okay. This is something I talked about in physics as well, which apparently is not really useful. What is an inertial reference frame? You remember?
So like the frame it's everything is 0 or something.
Yeah, you're getting the idea. So what specifically is the everything?
Point of view, relativity, something, I don't know.
No, you have the general idea, so you've got the conceptual understanding of it. The idea of a reference frame is that something within the reference frame, that the object that you're looking at within this reference frame has no net force on it. Okay, so I'll even put that on the board here. So if you have inertial reference frame. Says that the F net is equal to 0 on any given object. Okay. Now this is, let's take some examples. All right, within the classroom here. Outside. Who cares? You can hear me. The book that is sitting on the table here, its inertial reference frame I can take as the room. I can take as the building. I can take as the whole Earth for that matter. Because relative to the Earth, there is no net force on that book. Okay? There's a force of gravity that's pulling the book down. There's the normal force to the table that's pushing the book up. They cancel each other. So if we did a free body diagram, there's going to be forces on there. They cancel. The F net is 0. So we can call this its inertial reference frame where it's not moving. Now, give me an example of something that is in an inertial reference frame where the net forces on it is 0, but it is not the same reference frame as Earth, like the book in this case. In other words, the reference frame has to be moving with respect to Earth.
So like on a train or something?
Why not? On a train. So, Kyle's perfectly right. On a train, if you're moving along, okay, and you have your cup of coffee there, sitting right in front of you, the train is moving at 60 miles per hour. Hopefully your coffee's sitting still. You don't want that in your lap. That's McDonald's and the last one. Yeah, sorry. Took me down off train of thought. So the idea being is that on the train, if you have your coffee there, there's no net force, it is not moving. It is within an inertial reference frame. Now, the reason that matters is because we can conduct an inertial reference frame is to say that we can conduct all experiments with respect to that reference frame, and it should be exactly the same results as with respect to any other inertial reference frame it could be. Point being, okay, you guys have Hamilton or me, you guys all had the little ball launchers, projectile launchers. Launch the ball, and you predict how far it lands, right? Okay, so let's do that here on the ground, and we see how far it lands, we measure it, and we say, okay, it's 4.3 meters. Now, let's go take that up on a Boeing 747, okay? So we're now moving at 700 miles per hour, roughly, and we're going to, within the plane, launch it. Within the inertial reference plane of that object, which would be the plane, we would find that it would still land the 4.3 meters away. As far as our reference plane, we just launched that ball about 4 miles. I mean, that's what it's going to look like from our point of view. Okay, so that's the idea of the inertial reference frame. In intro physics, that we only just kind of talk about it and bring it up as this abstract concept, and we just kind of move on. We need to have that concrete now, because as far as special relativity goes, the reference frame that you're looking at something changes everything. All right, so whether we call it inertial reference frame or we just call it just inertial frame is fine. All right, so in 1905, Einstein postulated 2 things. These are the things that he postulated that would then forever change the way we look at things. Number 1. The form of each physical law is the same for all reference frames. All inertial reference frames. Okay, and that's exactly what we were talking about. The form of each physical law. Form of each physical law. I don't know what it was. So that's exactly what we're talking about right now. And the point being is that he was trying to expand this. He wanted to be able to say that within an inertial reference frame, whether we get to quantum mechanics or special relativity, that this is still true. Okay, so whatever else we come up with, so however we want to solve these problems, we want to say within an inertial frame that those laws still have to be true. So he was holding to this idea. And that's great, but then the second postulate screws everything else up. Okay. 2, second postulate states, light moves at the same speed to all observers. So that's the second. This was a problem, largely because it seems to be counterintuitive to the first one. If everything is, of all physical laws, stay the same within their inertial reference frame, how can light possibly stay moving in the same direction? Let's go back to the ball example that we just said a second ago. If I use the ball launcher here, I say it goes 4.3 meters. Okay. If I'm then just watching the ball, so I magically don't see the plane, don't see the launcher or anything. From the time I see the ball launch, the time I see it land, it has moved 4.3 miles because the damn plane is moving so fast. Okay? What he's saying is that is not true for light. Light moves at the same speed regardless to who the observer is. Okay. And we're going to try and prove that. Okay, the other thing, now let's talk about the first one actually, because that's a little bit easier. The first one is really important. The form of each physical law is the same in all inertial reference frames. There was this big push to find out the God frame, the God inertial frame. Say, okay, everything is not moving here, and we'll compare everything to here. To find out the Earth, and we'll find out, shit, we're spinning. Okay, fine. Then we'll look at the Sun. The Sun is staying still, we're not moving. Damn, the Sun is spinning around the galaxy. Like, all right, so then we'll take the solar system, rather. In the solar system's moving. Frick, no matter where we take it, we find that everything is moving toward everything else. Einstein's point of view came to the idea that all motion is relative. There is no such thing as absolute motion. There is no such thing as absolutely not moving. All inertial frames are equal to all other frames, such that all physics laws should be comparable to all of them. This was not something that was well accepted back then. It was just something that we adopt now. Okay. All motion is absolute. Oh, I'm sorry. No motion is absolute. All motion is relative. Okay, so now the idea of what we want to do is create a scenario. Wherever your book gives good scenarios, I'm sometimes going to pull examples from other books. But wherever they are good examples, I'm going to try and stick as closely as I can to the text. That way, in the event that you have no idea what I'm talking about, at least you go back and read what was written in there. All right, so we're going to take the textbook's example of Anna. Anna is a runner. Anna is a very, very fast runner. She's running at 0.2 speed of light, 0.2 c. That's her velocity. So we've got Anna running along here. That's really not that bad. All right, there's Anna going at 0.2 c. Okay, then we have fat lazy bastard who's just staring at her as she runs, hopefully for no perverted reasons. Velocity blue there. He's just standing there. Anna happens to be running with a flashlight because she's also a physicist. I really like that. Okay. Why is it waiting? Okay, let's just go straight up. So she's got this flashlight and she's shining it out as she's running at 0.2 c. The question is, when or how fast is the light moving with respect to Anna, and how fast is the light moving with respect to Bob?
Same.
Well, Einstein is saying it's the same. Now, from our point of view, we would say, no, classical mechanics says that well, we would just add it. So whatever the speed of light is. So Anna tells me that the speed of light is moving at c, 1c. So, from her point of view, this is moving at 1c. From his point of view, then it would have to be moving at 1.2c, right? Now, this assumes that light is a particle. All of Newtonian mechanics say that if light is a particle, then that's how that's going to work. Now, what if light instead is a wave? then what would it be moving? And how is it different?
Wait, it's a wave, wouldn't it still have the same effect?
No.
With sound class kind of did.
No, it
Is
isn't.
it treated like a sound wave? Like when
Yeah. Now, why is a sound wave different? Why does that matter?
Because once you make the sound from that point, it don't keep on traveling with you. It just
Right. This is an example that I show. See if I can't find a good one. Let's see if I do shift Doppler duck. Okay. This is about the best example we're going to get. I have no idea if this is going to record on there or not. But in any case, the idea is what we see here as on the duck is we see that the waves are the closest together here and they start to spread out farther and farther and farther, and they're going to be really spread out before. This is part of the Doppler effect. I was showing that before. Okay, if you've got a moving source, so, whatever the case might be, if here's our source, we're going to see that our waves are going to look like this as they expand out. Now this is the difference between particles moving and waves moving. When waves move, what determines the wave speed?
It's wavelength.
Well, here, let me give you guys an example. You guys all had me for 2212 except you. One of the things that I do is I have that giant spring. I crack myself one time. Remember we sent the amplitude along, went down the whole path, and we're back, and said, all right, we want to speed this thing up. How did I speed that up? Well, let's start off, what didn't work? Does anybody remember what didn't work? That's how I hurt myself.
Trying to do it really fast.
Yeah, I'm like, all right, I'll do it. You know, I'll add more force. I'll hit this thing as hard as I can. And then so I got a giant amplitude wave went down. And we timed it, for 5 cycles, so I gave someone a stopwatch. We found out that it went down and back the exact same amount of time. No matter how hard I hit that damn thing, it would not speed up.
Wasn't it the tension of the spring that changed
There
it?
you go. So the only way I was able to change the speed was to increase or decrease the tension. So now, at the time we were just talking about waves, and we we're just talking about springs and propagation, and I want to show you that the waves in the spring would change at the tension. But we're on to a bigger idea here. So if I wanted to speed up the speed of sound, okay, I'm in here, I want to, my sound, say I had a meter back there that was recording this, and I'm yelling into the meter, okay, I can yell louder, it's not going to freaking get in there any quicker. How could I possibly get it there quicker?
Change the medium.
Change the medium. How would I do that in terms of air?
Heat it up.
I gotta do something, right? So there's a lot of different options. You can heat it up, so add up the ambient temperature. That's going to change the medium. I could increase or decrease the pressure, basically forcing more air here, making more pressurized, or decreasing the air pressure here. In fact, if I increased it, then it would have more medium to go through and it would speed it up as it came through and back. Pretty sure about that. I have to think about it for a second to make sure that's true. But in either case, what you actually have to do is change the medium. When you're dealing with waves instead of particles, if a baseball is a particle, okay, it's not traveling as a wave. If I pitch the baseball, if I want to get you Kyle faster, I throw it harder, I apply more force. That's not true with waves. So, the idea being is that if you change the medium, you increase the wave. Let's get back to this. And this is also going to create the birth of something new. So, this idea of treating light as a particle was kind of a problem. Yeah.
Like I said, since it acts as a perfect wave both, is that why you can't get it to increase?
No.
Like you changed the medium.
No, you can't. Actually, anytime you change the medium, all it does is slow light down. So no, it's not the fact that it's the duality. The reason that it has duality, oh boy, I'm afraid to say this and not be entirely correct. A lot of it comes down to the fact that it's massless. It's a massless particle. So that's going to affect it. But we'll get back to the other idea as to why it can't go over the speed of light, or why we're limited to see. All right, so we'll get back to here and let's say, okay, now this is a sound wave, okay? And let's just pretend that she's got some sort of speaker that she's going with, and she's moving at this speed. Let's say instead it was 0.2 the speed of sound. In that case, what would happen is we'd see something like this. And we see that when we have spacecraft, when they actually hit the sound barrier, what they're doing is they hit that sonic boom, and if they travel exactly at the speed of sound, what ends up happening is that all of their sound waves are hitting right here. This is a terrible drawing. And you've got this giant sound front where all the sound just keeps building up there. So if you happen to be, as the spacecraft is getting to you, it's continuing to produce sound and it's adding up here. Okay, it's just this giant punch in the face, and that's why the sonic boom really is that powerful. So it can come by, yeah, it can easily blow your drums or anything else, knock all the windows out of your house, flies low enough. And bam, it can break a lot of things. A lot of energy stored in this. Okay, and if it moves faster, and I showed the video to, those of you guys from 2012, you can actually have sound trailing you, where the sound is actually behind you. So it's kind of neat stuff. All right, so that's the other choice. Let's go with that. Let's say that light is then a wave. Okay, so then the speed of light is dependent on the medium. So let's go back to the idea that Anna sees the light moving at the speed of light. She says, I've measured this, I'm really damn good at this, it's the speed of light, it's c. Awesome. That must mean that if light is a wave, that it is moving with c respect to this medium. Okay? So then, what should Bob be seeing, and why? Yeah.
Well, if it's based on medium, then you would say the same thing.
She's saying that she's seeing, I'm sorry, and maybe I should rephrase this. She's saying that, from her point of view, it is moving at c away from her. Away from her. I should, because it's from her own reference frame that it's moving away from her. Now, there's two choices with us. We can take it either direction. We can either say that this medium is moving or not moving. We can say it's not moving with respect to Bob or not moving with respect to Anna. Which one's of interest? Choose.
Anna sounds good.
Anna sounds good. All right. So then we're going to say that a reference frame here, an inertial reference frame, our medium, is moving at 0.2 c. The whole thing is going along like this. All right. So we're saying that if she sees the speed of light moving at c within the reference frame, so we've got light that moves at c within here with respect to that medium, then it's always going to be moving with respect to that medium. So with respect to this medium down here for Bob, it should be moving at c as well. But the problem is the medium is moving at the 0.2 c to begin with. So from Bob's point of view, it would still be 1.2 c. Now, if we did it the other way, and we did it as though it was for Bob, that the medium was still here, and she saw it as c moving here, even though she was moving 0.2 c, we would say that Bob is seeing it moving at 0.8 c. It would seem like it was slow. So no matter which way you do it, it doesn't add up. Whether you do it as a particle or whether you do it as a wave, neither one was adding up. And just to make things worse, when they actually did measurements of this, the question becomes, all right, she's shining this light, and they want to know, she says that as she's moving, and they actually have ways to measure this, which we're not going to go into, as she's running, measures the amount of time that it takes to get to here, and he measures the amount of time it takes to get to here, the exact same real point. They both say it's moving at c. Which one did they say it took longer to get here?
The one for Bob.
The same. That's the really weird part. From her point of view, she is running at 0.2 c, and this says it's going away from her at c. This guy says it's going away from him at c at the same time. Obviously, this one must be moving faster from our mental perspective. And when they time it, they say that they took the exact same amount of time to get here, assuming they both started their stopwatches right here. What is the only conclusion that this is possible? It has to do with their stopwatches.
Time is irrelative.
Say again?
Time is flexible.
Sort of.
Just gonna say time as well. Time is also relative.
Well, from what it's basically going to mean is that her stopwatch was actually moving faster for her than for his. The watch was actually going through time faster than his. So from both of their points of view, the exact, not from his point of view, her time was going faster for her. And it does get to this idea that time is relative. And this is why this was such a hard thing to conclude. They would run these experiments. We can run it as a particle. We can run it as a wave. We can say that it's a medium in the wave, which we thought that would solve the problem, because we've seen how this happens with sound. Okay, so it doesn't matter if the observer's moving, it has to do with the medium and how fast the medium's moving or not. But nevertheless, we still saw that light got here at the same time. The only possible answer to solve this is to say that time was different for Anna and than it is for Bob. And that turned out to actually be the case. But people didn't want to hold on to this idea. So instead, what they did was they created this idea of the ether. Okay? What air is to sound, ether is to light. So we figured that light can't propagate through nothing. It has to propagate through the ether. And it's the properties of this weird ether thing that somehow is going to make this work. In fact, today, even today, there are still scientists, very few, that still propose the idea of ether. And they want to bring this back. There was some evidence at the beginning. There were some things that lined up, not nearly enough, but they really liked this idea. I guess maybe it was hard to give up the idea that light doesn't need necessarily a medium to propagate through. Okay. And actually, I think we'll stop there, and then we'll get into the Michelson and Morley experiment on Tuesday. So.
Is Brett? Say, where's Brett?
Brad's not here. He's the reason we're recording.
I think you could be recording.
Yeah, actually, I did think he was going to be recording.
I'm sorry, so you should. I'll have to ask him.